SQLite is the most used database on Earth. It's in your car, it's in airplanes, it's even running on satellites in orbit. It really is everywhere. In fact, your phone is running several copies of it right now, just to keep track of small things like your contacts and your text messages. Most databases need their own server and someone to look after them. SQLite needs none of that. It fits a whole SQL database into one file. So today, let's open it up and see how it works, and why it ended up on almost every device we own. Here's the plan for the next few minutes. First, why SQLite is a library instead of a server. Then, how your SQL turns into a tiny program and the little machine that runs that program. Then the B trees where your data actually sits on disk. Then the trick that stops a power cut from wrecking everything. And finally, the one hard limit that tells you when not to reach for SQLite. Keep an eye on the bar up top. It shows where we are. Let's get started. When you use something like Postgres or MySQL, the database runs as its own separate program. Your app talks to it over the network. You open a connection, send your request across that network, and wait for the database to answer. SQLite skips all of that. It's just a small C library that runs inside your app. So, if you're writing a Python script or a little Node API, asking the database a question is nothing more than a normal function call. There are no connection pools to manage and no separate servers sitting in the background that could crash or run out of memory. Your tables, your schema, and all your data live in one file. And because that file is just plain bytes, you can treat it like any other file. Copy the whole database onto a USB stick or just email it to a coworker. To the database, your SQL is only a piece of text. So before it can run anything, SQLite has to turn that text into something it can execute. First, a tokenizer chops the text into small pieces. Then, a parser arranges those pieces into a tree and checks that the grammar makes sense. For example, that your select comes before your from. Once the tree checks out, a code generator turns it into bytecode. In other words, your query becomes a tiny program. And you can see this for yourself. Put the word explain in front of your query, and SQLite will print out the exact steps it plans to take. Instead of SQL words, you get real instructions with names like open read, rewind, column, and next. Your neat declarative query has been turned into a strict list of steps to follow, one after another. To run that bytecode, SQLite has its own little engine. It's a piece of software with its own memory slots, called registers, and its own pointers into your tables, called cursors. Think of it as a tiny virtual machine, a bit like the one that runs Java programs, but built purely for database work. For a simple select, the steps are very mechanical. The engine points a cursor at your table and moves to the first row. It reads the columns you asked for off the disk into its own memory. It hands one row back to your app, then jumps back and grabs the next row, over and over until it reaches the end of the table. Even a big join or a sort is really just a lot of these small steps stacked together. Everything above this engine thinks in SQL. Everything below it thinks in B trees. The engine is the exact spot where one turns into the other. Inside, the file is split into equal-sized blocks called pages. By default, each page is exactly 4,096 bytes. The page is the smallest unit SQLite reads or writes. It never grabs just one row from disk. It always reads the whole page that row sits in. Every table is stored as a B tree. To be exact, it's a B+ tree. Each row has an internal row number, and the real row data sits in the leaf nodes at the very bottom of the tree. Every index you add is simply its own separate B tree, one that maps the values in a column back to those internal row numbers. Why not a plain binary tree? Because it would be far too tall. You'd have to read dozens of pages off the disk just to find one row. A B tree fixes that by packing hundreds of keys into a single 4-kilobyte page. That gives it a huge branching factor, so the tree stays very shallow. A table with 1 billion rows is usually only about 4 levels deep, so one lookup costs just a handful of page reads. And the top levels of the tree usually stay in memory anyway. So finding a row often means just a single real read from the disk. Search an indexed column, and the engine walks 2 trees back to back, down the index to find the row number, then down the table to grab the row. The B tree layer never touches the disk itself. Instead, it asks a part called the pager for a page by number. If that page is already in the pager's memory cache, it hands it straight over. If not, the pager makes a system call to read it off the disk. The pager handles the hardest problem in all of database engineering. One transaction usually changes many pages, spread all over the file. If the power dies partway through, the file is left broken. The operating system only gives you a basic "write these bytes" command. But we need a promise that a change touching many pages either finishes completely or doesn't happen at all. A half-finished write can corrupt the whole database. Picture a bank transfer. The system writes the page that takes money out of your account, then loses power before it adds that money to the other account. The money just vanishes. SQLite solves this with a rollback journal. Before it changes any page in the main file, it copies the original page into a separate journal file, right next to your database. Then, to lock that copy in, it makes a system call named fsync on the journal. Normally, the operating system keeps writes in RAM for a while because memory is much faster than a disk. The fsync call forces it to stop and push those pages all the way down to the actual disk. Once that's done, the engine writes the new pages into the main database and calls fsync again. When everything is safely on the hardware, it deletes the journal. And if the power fails at any point in between, SQLite notices the leftover journal on the next start, copies the old pages back into the main file, and undoes the broken change completely. That fsync is the slowest part of the whole thing. The engine literally stops and waits for the hardware to confirm the write. It's slow, but that wait is exactly what keeps your data safe through a crash. The rollback journal has one big downside. To write new pages safely, the database needs an exclusive lock on the entire file, so readers and writers get in each other's way. If a background job is writing, anything trying to read has to wait, and your app can freeze. SQLite fixes this with write-ahead logging, usually just called wall mode. Instead of changing the main database, the engine adds the new versions of pages to a separate log file and leaves the main file alone during the transaction. When a reader needs a page, it checks the log first. If there's a newer copy there, it uses it. If not, it reads the original from the main file. Because the two are kept apart, readers and writers stop blocking each other. Eventually, those logged pages have to move into the main database. That step is called a checkpoint. SQLite does it on its own once the log gets big enough, around 1,000 pages, folding everything back into the main file and clearing the log. Even in wall mode, SQLite still allows only one write at a time. When you write, the engine hands out new pages and splits B-tree nodes into new branches. If two threads tried to reshape the same tree at once, they'd trample each other and break the internal links between pages. To prevent that, SQLite puts an exclusive write lock right at the engine. Writers have to take turns, and if one waits too long, your app gets a "database is busy" error. That's the real limit, one writer at a time. If you've got a normal app with a handful of users, SQLite handles it with ease. But if you've got 50 servers all pounding one shared file over a network, you've picked the wrong tool. The people who built SQLite say this plainly. It isn't trying to replace Postgres. It's trying to replace writing to a plain local file. Let's tie it together. When you run a query, your SQL is compiled into bytecode, and a small virtual machine runs those steps against the B trees in your file. Below all of that, the pager makes sure a power cut can't destroy your data. And the whole thing lives in one file on your disk. No server, no setup, no network. That's exactly why SQLite ended up in just about every device you own. And if SQLite ever comes up in an interview, here are 5 questions worth thinking about. Pause the video and see how many you can answer. Each one points back to something we just covered. 1. Why does SQLite compile your SQL into bytecode and run it on a virtual machine, instead of just running the query directly? 2. Why is table data kept in a B+ tree instead of a plain binary tree, and what does that flat shape give you? 3. What does the fsync system call actually promise, and why is it the slowest part of a write? 4. What problem does wall mode solve that the rollback journal couldn't? 5. Why does SQLite allow only one writer at a time? And when does that make it the wrong tool? If you enjoyed this, drop a like and subscribe. It genuinely helps. And tell me in the comments what we should open the hood on next.